another story, something to get off my chest.
Hello, this is a live presentation for the Pyper podcasts. Difference is today I gave a presentation to a group of individuals. I recorded the sounds whilst I presented and essentially superimposed them over the PowerPoints. I hope you enjoy it. Okay, so today, as requested, we're going to talk about antibiotics. So Santos wanted to know the different types of antibiotics, what they do, how you choose between them, the different actions that they have. So essentially, we're starting off with this, and the next two that you guys will be here for, the Americans, you've asked to go over more pharmacology side of the house, because it's not, especially primary healthcare, and it's not been a big part of the actual training that you guys do. So the focus of today is we're going to go through the 7 groups of antibiotics, talk about their mode of action, what they do in order to kill the bacteria, and why there is so many different types. And then you'll have a general understanding of each class and essentially the major signs and symptoms and things to look out for each of them. What we're not going to cover is we're not going to cover specific conditions with specific regime of antibiotics. The reason is because we all have protocols, we all have people that we need to call in order to get those prescriptions. So it's different across the nations. So for me to stand up here and say what we do in Australia, it is going to be different with the UK and the Americans as well. So it would just be an idea of why the antibiotics works for those particular classes, and then that's essentially it. So 3 ways in all antibiotics work. Okay, they're either selective, that they can penetrate the cell wall, or they are involved in dissolving the cell wall of the bacteria, causing it to explode, or they affect something known as protein synthesis, or certain antibiotics will actually affect the way in which the bacterial DNA acts as well. So there are 3 different ways. That's it. That is as simple as antibiotics work. So each of them are either classified as a bactericidal antibiotic or a bacteriostatic antibiotic. The difference is obviously bactericidal will kill the bacteria, and bacteriostatic will essentially stop it going through its reproduction or growing process. Now, every antibiotic actually relies on your immune system to work with it. Okay, so even in the case of bactericidal, when the bacteria is literally being broken apart, the body still needs to have a relatively good immune system in order to clear up all the toxins and all the leftover organelles within the bacteria. So if you're having a choice, if someone has a relatively poor immune system, then bactericidals are going to be better. Bacteriostatics essentially will hold the bacteria at bay, allowing your immune system to come in and take care of the rest. So that's the main difference. So you may be asking, if there's only 2 different types and 3 ways that they work, why is there so many antibiotics on the market? Now you could assume that it's got to do with money making, and I suppose a little bit is that, but things that we have to take into account is bacteria within the human body is not as simple as it may seem. So we have something known as bioavailability. Now that term essentially means how much of the actual active ingredient is going to get to the area that it's needed. So if you imagine you've got an infection in different parts of the body, certain aspects are going to be difficult to penetrate compared to others. Okay, if you have areas of the body like the bladder, it's not very good vascular, can't have good infiltration, then it's going to be difficult for the antibiotic to actually get there. So that's why there's so many varieties available, is because where the affections lie. We also have something known as resistance that we'll talk about with each particular strain, in particular the most popular one. It's quite resistant, and it means we have to improve the way that we design antibiotics in order to counteract the actual bacterial mutation. Now, there's only about 100 different bacteria that affect the human body. Okay, so in retrospect, that's not a lot, because there's probably 10,000 species of bacteria in total, and only around 100 of those will actually cause some form of pathogenesis within our body. So ratio-wise, it's not that bad. But each one of those species of antibiotics has the ability to mutate. It has the ability to change slightly, has the ability to gain resistance. The way that they gain resistance and alter themselves is the same way in which all animals go through evolution. So it's just a simple process of survival of the fittest. As you can imagine, we are killing trillions and trillions of bacteria every day. So we are essentially expediting their evolutionary chain. Okay, for the same thing that happened with any other mammal, so it would have to be a global incident. It will cause many of us to die, and then only the strongest to survive. We're essentially doing that every time we give antibiotics. So resistance is more probable than in other species. Okay. So when you have a particularly resistant strand of bacterial infection, sensitivity or specificity is very important. So that's where we actually get the bacteria tested in the lab to see which of those classes is actually going to kill that bacteria. So we often start guessing at first, most probable, but then if it comes back resistant, they've still got infection, then we will need to test the bacteria in a lab to see which of the antibiotics are going to kill it. Otherwise, essentially, it just won't work, and you'll find out more. So, first off the rank is our most popular. This is the one that you guys will know the most, which is your beta-lactam antibiotic. Okay, this is by far the most common and readily used of all the antibiotics. Okay, you'll see the list here. So all of your penicillins, all your cephalosporins, and your carbamazepines as well. Okay, carbamazepine is obviously as popular, but everyone knows of these particular antibiotics. You just probably didn't know that they were called in the family of the beta-lactam group. Okay, so keep those in mind as we go through how this one actually works. So this one is a bactericidal, one of the few bactericidals that are actually around as far as a class group goes, and it works by essentially attacking the cell wall itself. Okay, so to break that down, it's mostly affecting all of what's known as gram-positive bacteria. So if you have certain species, some are stained gram-positives, some are stained gram-negatives. They're also referred to as anaerobic or aerobic. It's essentially a way of how they get their energy sources. So gram-positive bacteria have an enormous internal osmotic pressure. And in order to counteract that, they have an external cell membrane that essentially keeps themselves in bay. So think of a kiddie pool filled with water, and that's essentially your gram-positive bacteria. What beta-lactam does is it actually binds to something known as your penicillin, penicillin BPP, so penicillin-bound peptides. And what they do is they essentially join amino acids together in the cell membrane, and that essentially makes it strong. So beta-lactam ring will actually connect to that PBP, and essentially stop that connection of those amino acids. By doing that, it weakens the outer cell membrane, and because of the internal osmotic pressure, the bacteria essentially blows up and dies. So it falls apart. Much the same as you getting your kiddie pool and cutting a knife through the outside wall. It's just going to explode. So that is what your beta-lactam does. Almost that's why it's one of the most popular and most vast used as well. It's very effective. So because of its wide group that has all those penicillins, all those cephalosporins, it's used for an extremely wide variety of bacteria. Essentially anything with a strong cell wall is susceptible to your beta-lactams. Okay, mostly gram-positive and mostly your anaerobic bacteria, okay, but it does work on certain species of negative as well. As far as how good it is, because it's so broad, it depends on which antibiotic you specifically use for which type of infection. Now there is a probability that some of the bacteria can get resistance. What they do is they actually end up creating their own enzyme, is the bacteria, called beta-lactamase, and what that does is it sits in that penicillin binder. So therefore the beta-lactam ring can't get inside it, and then all of a sudden they can still clamp the cell wall off. So it basically renders the beta-lactam completely useless. That is why we've added certain agents like your caveolatic acid, which essentially will come along, it will remove the beta-lactamase, and then all of a sudden the ring can work as normal. Okay, so when you look at things like augmentin versus augmentin duo, augmentin is just your simple beta-lactam without the caveolatic acid. You move into your duo, then all of a sudden you have that caveolatic acid that can come along and beat that resistance. Ones that we classically use that in is if we start with amoxicillin or something like that, or for a sinus infection, and they go for the regime, it doesn't seem to work. Essentially what that can mean is the resistant bugs are left, so then we give them a duo first. Now unfortunately most people go straight for the one with caveolatic acid, essentially place their bets, which whilst in theory will obviously work against all of them, it just essentially increases the probability of the next mutation. It's like a massive arms race, if you imagine. Okay, so that's your broad beta-lactams. Any question on those? Because they're the ones that you're definitely going to see the most around. All good? Rightio. Adverse effects, not very many, which is fantastic. So whilst they're widely used, there's not a lot of bad adverse effects as well. So the main problem that people come along with is obviously if you have an allergy to penicillin, then essentially the whole beta-lactam group is essentially ruled out. Okay, so we all know the link with penicillins and cephalosporins. If you have allergies to penicillin, it's recommended not to give cephalosporins as well. So if you have that allergy, then you will have to choose a different antibiotic, which we'll move along to. But generally speaking, they're safe. Problem is if someone has a sensitivity to amoxicillin, then they're probably going to have a sensitivity to the entire range as well because of the action that it has being similar. Okay, the only difference in the actual tablets themselves is their tissue penetration or their bioavailability for certain tissue. That's it. Okay, so it is safe to use. It's often used in small doses over an extended period of time. So this antibiotic we give in your 7-10 days sort of regime. Because it takes those small doses, takes those serum levels to be up in order for it to work. Things that you have to take into account is certain ones will take about 3 days for the serum levels to get up before they'll actually become effective. And if you miss a single dose, then your serum levels will drop and you have to try to build them up again. So it's very important that you take those actual antibiotics as directed and you instruct the patients to do so as well. So there's your summary. Pretty much gone through it. One of the only bactericidals, very, very wide use, relatively safe. You do have to be careful of allergies or sensitivities because it's across the board, and you don't need to monitor any blood volumes or any renal failure or anything like that with these particular ones. Okay, so they are good to use, good choice, and most likely will be the most probable one that you guys will get to carry when you're in the field by yourself as well, because they are vast and pretty safe as well.
Do most variations of penicillin have a suffix of cillin?
Most, yeah. So cillin do, yeah. All those cillins do, unless you're using brand names, then they come up with whatever they want.
Mm-hmm.
But as far as the chemical goes, yeah, they'll have that cillin, same as sporins. They will often have that sporin at the end, and you'll see other similarities with the other groups as well.
Mm.
It does make it a little bit easier. There's one that's confusing that we'll get to, but that's okay. Okay, next one on the common list, if you will, these are your aminoglycosides. So these are more of your hard-hitting ones. Okay, if you look down the list, you'll see a few names that you'll know. You've probably all seen neomycin, you've seen gentamicin before. Okay, often given in conjunction with your beta-lactams. Okay, so these ones are essentially a completely different group and they act a completely different way as well. So the action of these particular ones is they're involved in stopping protein synthesis. Okay, so what the antibiotic will actually do is it will come along and it will sit on the main part, or the building part of the ribosome, and essentially stop protein synthesis. So the difference with this one compared to the other ones that you'll see is your aminoglycosides will actually bind to the messenger RNA chain and essentially not move. They will find a binding site and they will sit there, and therefore stopping the creation of peptides. So just as a bit of revision, the ribosomes within a cell are responsible for all peptide creation. The ribosomes are what makes amino acid chains, and amino acid chains are essentially everything within the cellular body. As far as enzymes go, DNA goes, it all essentially comes through the ribosome in order to be read and created. So if you imagine if you have something that is irreversibly blocking that messenger RNA chain, then as the base nucleotides come along to bind the amino acids, it's essentially going to miss a step, meaning that peptide is completely useless. What that means is the bacteria isn't actually able to double itself internally, and therefore it can't go through binary fusion, and therefore it can't multiply. So however numbers you have inside you is however many you're going to have until your immune system comes along and takes care of it. Okay, so that's essentially how these particular ones work. Now they do have a very narrow spectrum of use. Okay, luckily the reason we want to use these ones is because they're slightly better at getting to those hard to reach places, and they're all about your aerobes. Okay, so they do not affect your anaerobic type bugs. They're more of your cell wall based ones, but your aerobic type bacteria, they're very susceptible to these particular ones. Okay, that causes bacteriostatic. Okay, so a few names that you'll know: Pseudomonas, E. coli, those sort of ones. They essentially are highly susceptible. Most of the time, we give an aminoglycoside with a beta-lactam as well. So then it can hold certain ones at bay whilst the cell walls are being destroyed as well. So it's a sort of a fight of stopping reproduction as well as destroying it, okay, for certain types. Now, we do have to be excessively careful when giving these particular ones, okay? So they're usually a high dose, one-off, but they have big warning signs associated with them. So they are nephrotoxic, incredibly, and there's a lot of warning associated with people with renal problems, or if they're already on a nephrotoxic drug, you have to be very, very careful with these particular antibiotics. Also, we don't often give them high doses or a prolonged course of these particular ones as well without really assessing their kidney function. The more you give them, the more nephrotoxic substances there are, and then obviously that. Another unusual one, mostly you'll find with the gentamicin, is an effect on the 8th cranial nerve. Okay, so people can end up with irreversible vertigo as a result of taking high-dose gentamicin. Okay, we've actually had people in the military that have been downgraded and removed because of a one-off dose of gentamicin, and then essentially irreversible vertigo. They can't function from then on. So it's something you have to take into account. The other one, especially when mixed with anesthetics, or if you were to push any of these drugs rapidly through IV, so a lot of these are very slow push drugs when you're giving them. So if you push it in as a bolus, then you increase the likelihood of neuromuscular paralysis. And you can actually generate an autoimmune disease that causes skeletal damage as well. So yeah, pretty nasty. Now, not to say that we never use them, but just understand that they can have side effects, and we need to take those side effects into account, and then really look at someone's hydration status and renal function in particular, and also whatever drugs they're on, so we don't have a compound effect. That's essentially what it comes down to. Okay, so that's that. These ones, if someone is on them, they should be monitored. Their kidney function should be monitored, and we should always avoid use if someone has renal or hepatic failure as well. So, summary: all aerobes, very toxic, usually given as a one-off dose in conjunction with your beta-lactams. Okay, they're fantastic for UTIs. Imagine, because they have such an effect on the kidney, it means a lot of that actual antibiotic is still going to be bioavailable by the time it gets to the bladder. The bladder being one of the really hard places to fixed infection, so these particular classes will survive all the way into the bladder. Having said that, they have terrible penetrating ability. So if you have a joint infection, CSF infection, lungs, anything like that, essentially these antibiotics will be pretty useless. Okay? Right, yeah. Next cab off the rank, everybody's favourite, macrolides. It's just cool to say, little macrolides. Okay, completely different class. You'll see that they respond very, very similarly to the last one. You guys are all over it. Okay, so these ones here, they have a lactone ring, but they don't work the same way as the beta-lactam. That's why they're so much fun. Okay, they actually have a similar effect to the aminoglycopeptide. Okay, so very common ones that you would have seen before: erythromycin and azithromycin. Okay, same name as gentamicin. So you can get a little bit confusing because they all end in myosin, but they are different. Okay, you may, based on the next slide, you may go, bullshit, they're exactly the same. Okay, because they too stop RNA-dependent protein synthesis. Okay, but they are different because these particular ones are bacteriostatic mostly, but they can be used as a bactericidal as well. Now the difference between these two, you may be looking at the picture saying that's the exact same picture, is where the actual antibiotic responds. So the last one would irreversibly sit on the 30S substructure and just basically block the production of the amino acid or the peptide. Your macrolide is actually responsible for blocking the amino acid bond at the top. And it's not irreversibly, so it can actually float around within the organism and block multiple as opposed to just one. So every time it meets a particular strain of amino acids, whenever two of those will join together, then it'll essentially break that bond, rendering the peptide useless. Okay, so that's what it does. The reason it can be used as a bactericidal, as well as if you give a higher dose into a cell and it's breaking multiple peptides, what will actually happen is the organism itself will start seeing itself as a non-self, a lot of selves there, but a non-self, and then activate its lysomes to kill itself. So that's why it's bactericidal at higher doses. So that's the difference. Okay, I know a lot of similarities between the way it works, but remember what it says, it's got to do with the area that it can get to, the bacteria that it can form, and any resistance and increase tissue penetration as well for these ones. Okay, so not surprising, it's your aerobes as well, okay, because it's similar. Okay, but this one here is better when you're dealing with lung infections as well, because it has that increased tissue penetration ability. Okay. So it's a really good one for your tonsillitis, pharyngitis, pneumonias. Can be pretty good with this one as well, okay, because it has that increased penetrating ability with similar function to the last one. Okay. On top of those, it can also be used for pretty much any soft tissue. So into the joints, great for cellulitis, and really good choice for your STIs as well. Okay, a single dose of azithromycin is pretty good for your chlamydia and your gonorrhea as well.
Sure.
I know, pretty good. That's a good one for you, UK. Okay, remember that one. Only dose.
Oh, I already know about that.
Yeah, I'm sure. I'm sure.
My guys
So-
know about that.
I'm sure. They probably have it in their pocket.
You guys are the reason we know about it.
Not surprised though.
So this one here is safer than the last one as well. Remember the last one we talked about that had the ribosome effect, and essentially it's quite toxic. This one here is all hepatic elimination, so it doesn't actually, it's not as harsh on the kidneys as well, so therefore it can be, and also a good choice for anybody with renal problems. Okay, the main side effects you'll get with these ones, and anyone who had it can attest to it, is you have gastrointestinal upset with it, so you will feel very sick most of the time. Okay, as far as 33% as far as the side effect goes is a pretty high side effect rate for a particular drug. Okay, as mentioned, it's great for your lungs. It has really good tissue penetrating ability, and it's a really good choice if anybody has a penicillin allergy as well. Okay, because this does affect gram-positive and negatives, therefore it can assist where the beta-lactam can't. Okay, so we'll move on to our Fluoroquinolones, another class of bacteria, antibiotic that works again slightly different. The ones you guys will be most familiar with is ciprofloxacin, levofloxacin. Okay, we've been giving those out like they're friggin' Skittles in this particular deployment, so you can probably guess what they're pretty good for as well, just by that. So the way these work is completely different again. So these are one of the most unique type of antibiotics that these will actually affect the DNA chain itself. So unlike the protein synthesis ones that essentially will stop your peptide production, they will stop any enzymes that are used in affecting DNA, but it won't actually touch the DNA itself. With a lot of bacteria, when you're dealing with the DNA change, they have a double helix, but they don't have chromosomes like us. They have essentially plasmids, essentially rings of DNA that basically float around freely, so they're not free to a nucleus itself. So your Fluoroquinolones will actually come along, and when the DNA is separating in order to reproduce itself, in order to make a new species, it will actually come along and affect the DNA gyrus. Essentially, it's the area of the DNA that will spin, just like a gyrus, and separate the DNA in order for the messenger RNA to come along and create a subsequent strain of plasmids in order to create a new bacteria. This will essentially stop that production. Therefore, the DNA can't split, it can't reproduce itself, and that's it. Okay. On top of that, if certain bacteria have already started splitting before the antibiotic gets there, it won't actually allow it to rejoin as well. It won't let it finish the process, and it will also stop it from repairing any damage too. So it essentially stops all reproduction and function of the DNA strain itself.
Poly 2ED.
So looking at that, what would you classify this particular antibiotic as? A static or a cidal? Static. Excellent. So it stops that binary fission that occurs with bacteria. Okay, it's effective on all gram-positives. So it's a really good one. One of the main reasons that we use it here is because we know that the short regime is going to work on the myriad of different bacteria that can be causing a gastroenteritis. Okay, it is also effective on the gram-negatives. So if you do have a Pseudomonas infection, then it can also work with that. If you are using your ciprofloxacin, then that essentially has the best bioavailability of the whole class. Okay, so it's a slightly larger regime, as we know, but it has much better bioavailability. If we have any resistant strains as well that aren't affected by the other antibiotics, it can be a good choice as well because of its attack on the DNA. So if you imagine we use a different bacteria that's already attacked the RNA, doesn't work, already attacked the cell walls, doesn't work, this one here can be a good alternative for those different atypical bacteria because of its ability to affect DNA, which all bacteria have. So in summary, great for a huge amount of antibiotics. A huge amount of bacteria. It has incredible bioavailability, so it actually gets into the bacteria themselves. It's good with UTIs involving E. coli, so usually your urethritis, things like that. Okay, it's a really good choice for. And it's good if you have a sepsis caused by any intra-abdominal problems as well. So the reason we specified those ones is because it has the ability to essentially not be affected until it reaches the area of the stomach, whether it's small intestine that's causing the problem, the sepsis, large or stomach, and it also has a good ability to get to the kidneys without being affected by anything else. Okay, so it can essentially get anywhere it needs to in the tissues without being broken down, which is why it has an outstanding bioavailability. And it doesn't really rely on having to do sensitivity tests because all of your bacteria will have DNA. The only bacteria that aren't susceptible to it is essentially the one that the fluoroquinolones can't get in to. That's it. So really good choice, hence why we use it so much. Okay, another one, very unique sort of one. We all know this one. Okay, is your tetracyclines. So most commonly, doxycycline. Okay, now obviously we use our doxycycline mostly these days as a malarial prophylactic, but it's still a reasonable choice for your bacterial infections as well. Now the way your tetracyclines work, again, is a slightly different version of the other ones. Okay, so remember our aminoglycosides would actually sit there irreversibly and block one chain, never move. Okay, this one here will come along and it reversibly binds to it. So essentially will come along and as soon as it finds a particular trinucleic group, it can bind to any one of those as they're activated. So this one will come along and it will bind independently, therefore stopping many peptide productions as opposed to just one. Okay, like your macrolides. So that's essentially the different. And it's the exact same process as the rest, stops the peptide production, therefore stops the reproduction of the bacteria. So it's a bacterial static. The reason we need these slightly different types is again the slightly different species, the bioavailability in tissues, so we need the variety in order to fight the different areas and the different species of bacteria. Okay, it is good on your cocci and rods bacteria. Okay, so essentially if you look at species and structures of bacteria, they're defined by their shape. So this particular tetracyclines are good for your cocci and your rod-shaped bacteria. Okay, they also have effect on gram-negative and positive, so they're quite broad spectrum, and they've been found to have really good killing ability or static ability for your unique ones. Okay, so your mycoplasmas, Rickettsia, and protozoa like your plasmodiums that you get from malaria. Whilst it doesn't obviously kill it, we know that, it keeps it at bay in the liver, preventing it to mutate to its erythrocytic phase. Okay, so it's a very, very broad spectrum antibiotic, as we all know. It affects, okay, we've all been on it, so we all know the effects can be pretty crap. So esophageal ulceration, what do we tell people to do when they're on doxycycline? To prevent that top one?
Don't take it and then go to bed.
Don't take it and then go to bed. Exactly right. Go to bed, you lie down, it sits and dissolves at the edge of the esophagus and you get the ulceration. It's also recommended with food, so I think because of that one. Photosensitivity, yeah, we all know photosensitivity. It happens, especially this whiteys anyway, because we're already photosensitive. Take doxycycline, you get worse. Now doxycycline and pretty much all tetracyclines should not be given to children or babies or pregnant women because tetracyclines have a unique ability to bind to infant teeth and infant bones because obviously they're quite different in structure. They don't have the outer compact layer that we have, so it can actually penetrate them and then weaken and tarnish the actual bones and teeth itself. So avoid pregnancy completely and avoid giving tetracyclines to children as a pretty good side effect. Right, yeah. Reason we choose it over the other ones, even with a similar effect, use it compared to your aminos in particular, is because of its tissue penetration. So if you have soft tissue infection like an abscess, this is a perfect choice. If you have resistant chlamydia, really good choice as well. Because it has that ability to get to the area that the other antibodies can't, basically. Right, questions on those? Quite unique. We're getting pretty specific now, especially this one here, okay? Glycopeptides. This is a new brand of antibiotic, okay? Obviously not relatively new, but compared to the others, it's quite new, okay? Most common one is obviously vancomycin, okay? So you could probably guess why we use this one, but we'll go through it anyway. Okay, this one here finally has a similar effect to your beta-lactam, so it will actually affect the cell wall. The reason, it does it differently. So whilst the beta-lactam will affect the penicillin binding agent, this particular one here will actually sit on the walls of the amino acids and therefore prevent them from sticking together, regardless of what sort of binding agents are there, regardless of what sort of resistance is within the binding agent. It bypasses that and it attacks the actual cell wall itself, and it stops the hardening formation at the amino acid chains. Okay, so it's very hard to establish resistance for vancomycin compared to your beta-lactams. Okay, that's why vancomycin is often your second line that you use if your first one doesn't work. Okay, and it's really good for resistant type bacteria as well. Okay, so that's essentially what it does. Okay, it is enormous. Okay, so it obviously does have a bit of an effect on the kidneys. It's only active against the gram-positives. Gram-positives have the right sort of cell wall that this works with. Okay, but that's fine because like your beta-lactams, gram-positive, this is what it's used for as well. So like I said, second choice, unless you have confirmed MRSA, okay, or C. diff. Okay, C. diff is a particularly resistant one as well, very hard to get the bioavailability to kill it. Vancomycin is an excellent choice. Okay, it's obviously used for a lot of ortho problems as well, ortho surgery, that sort of thing, because of its penetrating ability and because of its ability to bypass any resistance at this stage as well. So it's a really good choice in all. Okay. And the last one we'll talk about is your metronidazole. Okay, slightly different again. This one here is again often used as a second line of defense. And this one here is particularly good at killing any bacteria that has a flagellum. And what that means is the ability to swim. Okay, so certain bacteria have a tail, which means you can freely move around and in a lot of cases avoid the actual antibiotic. That's essentially what it can do. It can go to an area that the antibiotic can't reach. It can move to an area that's not under attack, all that sort of thing. So metronidazole is really good at certain bacteria, so it's an antibiotic. It's a amoebic cidal as well. Okay, so any amoeba, which is essentially larger single cell organisms that can move, and it's also good for your antiprotozoal as well. So very, very good for any protozoa with a tail as well. Most famous, Schistosomiasis as well. All right, so metronidazole's good. Anything else we use metronidazole for commonly? You remember? Right, side project for you. It's pretty commonly used for things like that. I'll let you think about it. Okay, the way it works again, this one is super cool as far as a scientific or biological point of view. What it does is metronidazole has the ability to come into the cell, so it comes into the cell, then it will actually steal part of the process that's involved in DNA restabilization or synthesis, and from there it actually binds that part to itself and becomes a free radical. And as a free radical, it changes the internal structure of the bacteria, causing it to kill itself. So pretty damn cool, eh? Very clever. Right, so different to the rest, which is why it's a great second line sort of drug. So it works, as you can imagine, on those anaerobic type ones that move around, don't need oxygen in order to gain energy. It's fantastic for bacterial vaginosis, good penetrating. C. diff again, if you have a resistant one, and also pelvic inflammatory disease, just because of the essentially their aerobic nature. It's all internal, nothing's getting to it, so that's where they thrive. So metronidazole is really good for that, and particularly gastrointestinal problems that are resistant as well. Okay, so that's your metronidazole. So there's your 7 classes. As I said, we're not going to go through specific disorders, specific antibiotics, because it's essentially, well, one, you're not likely to remember because there's too many regimes. That's why we have books. That's why we have protocols. But it's good to understand what they do, essentially, so then you can figure it out. Side effects easier, pathophysiology, pharmacology, pharmacokinetics. It all makes sense if we understand how the structures work. But just as a general overview, the most common 2, beta-lactams are fantastic for most problems. Okay, so they are a really good starting point for an antibiotic, unless you are certain it's a certain pathogen. Okay, so it's great, soft tissue, has slight penetrating ability, not the best. Okay, it does not work on abscesses at all. So abscesses is one of the hardest ones to get rid of. Abscesses turn into cellulitis, cellulitis turns into sepsis. So don't pay particular point to abscess that you'll find, because neither of these are good for that. Your aminoglycosides are really good for anywhere that blood flows to. Okay, but it has terrible penetrating ability, and as we've already mentioned, can be quite toxic. So it's a good supportive agent for any infection that's involving highly vascular organs, that sort of thing. Okay? It is terrible at anything that is essentially not connected directly to the bloodstream. It has poor penetrating ability. If you want penetrating power, then you look at your other ones. If you have an area that is difficult to get to, or if you have a particularly resistant one that's not responding, then we move to tetracyclic macrolides, fluoroquinolones, or in particular, your clindamycin has much better penetrating ability. Okay, so that's essentially the overview of different parts of the body, of what different types of bacteria we pick up. When you're dealing with antibiotics and bacteria, we always have to be mindful of the prospect of sepsis occurring. Okay, so obviously sepsis is a systemic problem, and it has the ability to essentially kill people. This is essentially the early signs or the starting point of shock, which eventually is how people die from infections. So we need to identify it early. Now, there's a few methods out there in order to identify, and if anyone's been following the sepsis campaign, the early goal-directed therapy, early intervention regime that's been going around for the last 5 years, you'll know that there's a lot of differences associated with treating sepsis. Finding sepsis is essentially hasn't really changed that much, since this one came out years ago. Okay, and this is the SIRS criteria. SIRS is systemic inflammatory response syndrome, and it's essentially what happens when bacteria infiltrate the body and then start to affect it on a much larger scale compared to isolated. Now, the way bacteria affects the human body, for purely interest, is as it metabolizes or as it grows and changes, it releases cytotoxins. Cytotoxins invoke an inflammatory response, and you get that problem. Different types of bacteria will actually use you as its organic fuel. So it'll actually start eating you away, and in the process cause prostaglandin and a systemic inflammatory response. From that inflammatory response, we get those septic sort of signs and symptoms. The profound vasodilation thanks to overwhelming of prostaglandin and by bypass histamine response. Obviously, vasodilation, decreased perfusion status, increased heart rate, that sort of thing. You get quite acidotic as a result, so your rest rate will increase. One or two things happen. Early signs, you'll get a high temperature because of the release of pyrites in the initial inflammatory phase, or you'll get a lower temperature, cold sepsis, because of the already starting vasodilation, which essentially is hemorrhaging heat from your body. Okay? In a healthy body that has white blood cells, they're going to go haywire. They're going to be reproduced and then essentially you're going to have a much higher concentration as well. So because of that, that's our SIRS criteria. We look at the temperature, high or low, consider it. Look at the heart rate, above 90. Rest rate above 20. These are all signs of compensation, early acidotic states, and white blood cell count as well. Now, if this is different in particular nations, then just look it up, depending how you quantify blood cells itself. Okay, so that is SIRS criteria. If you have 2 or more of those, you meet SIRS criteria and essentially invokes a different, you need further investigation. That's what it means. It doesn't mean the person has sepsis if they have a SIRS criteria. It just means that we need further investigation. So for every single patient we see, we're going to get 3 out of those. And if you definitely have a good one, like a temperature, it's recommended to get a blood test. But if you have any of the 2 or above, then you at least consider that the person could be sepsis. And sepsis is essentially defined, it changes across protocol, but essentially, general consensus is it's SIRS plus a suspicion or confirmed infection. So we start looking at the chest, looking at the abdomen, looking at the skin, ears, throat, that sort of thing to try to find that sign of infection. Okay, and that is sepsis. Septic shock is obviously with the shock phase as well. Okay, so lack of oxygen, lack of perfusion. Too easy? So never forget those ones. This is the important part of bacteria and antibiotics. Okay. So what do we need to take away from this? Essentially, you don't have any regimes, you all have protocols. Okay, so utilize those. So hopefully what you got out of this is an idea of why we have so many different types of antibiotics and the way they work on the body. So when you're looking at somebody and you're doing your patient examination, think about the type of infection. So think about where it is, if it's going to be difficult to get to, therefore tissue penetrating or not, and think about which antibiotics will most likely affect those areas, either aerobic areas or anaerobic areas as well. From there, try to match the 2 with a type of antibiotic. Check your protocols, and then always, wherever possible, talk to the prescriber. Okay? Not very often there's only a few cases where giving antibiotics in an emergent case is obviously our job, okay, and that's your ceftriaxone for confirmed sepsis, any traumatic blast, meningitis, things like that, and it's all in our protocols to give ceftriaxone. Everything else, essentially we have time. We have time to contact, we have time to read, so look up the best regime and then go from there, okay? Before you're giving any medication, especially antibiotics, always look at if it reacts with something that they're on as well, okay? In particular, your Aminoglycosides as well, right? They're obviously the big dangerous ones, and realistically you shouldn't be pushing those too much anyway.
And for females, if they're on the pill.
Yep, excellent point. It definitely reacts with the pill. So look it up. We do not expect people to keep this stuff in our head. That's why we have books, that's why we have protocols. So understanding the pharmacology behind it essentially can help with the knowledge later on. Okay? So that's it. Is there any questions at all of what we covered? Happy with that? What we're looking for? Okay. Well, I hope you enjoyed the first live presentation. I apologise about the quiet sound in the middle there. I'll try to get a better recorder. But until next time, take care.